Welcome back to another episode of Pollys Introduction to Computer Networks. So the announcement today includes the links for the lecture video as well as the Google Meet session. And this week, we have only one quiz due by Saturday. And that's because exam 1 is coming tomorrow. If you click into the exam 1 channel, you will see all these things that you want to be aware of taking the exam. I think Polly went through the first set of the instructions, including the exam scope that is posted already last week, as well as how challenging Google CAPTCHA could be. So it can sometimes take rounds to complete the CAPTCHA. And Polly posted more, and this is to tell you more the whole process, how it's going to be like. There'll be things that you will need to complete or you need to be aware of before the exam. So for example, the PA workstation firewall is going to be off starting today. And then there's a individual exam accounts, that's using your student ID. That's going to be ready also starting today. And tomorrow morning, the first thing we need to do is to check your student ID. So you will have to show your student ID with the photo side, of course, and so I can match the photo and your face from the camera. And then Polly would pronounce that the exam begins, and then there's going to be a 10-second countdown in the end. By the way, your exam, the Google form there comes with the timestamp. So Polly can tell when is the last time you submit. So you want to submit within the time limit. It might be, we might give you a 2 to 5 seconds grace period, but that's all. So it's best that you submit at least once a minute before. And if Polly is starting counting down, definitely submit the last time. And even though tomorrow we'll start the exam 10:20, and we say that we end the exam at 12:10, but the exam duration, starting from the time Polly says the exam begins to the end of the exam, that duration is 90 minutes. So we might be able to end the exam a few minutes before 12:10. So 12:10 is not the time you can last submit. The exact time you can last submit, Polly will also type that up on the Google Meet chat box. So tomorrow you want to work on the exam, work on the Google form. You also want to pay attention to what Polly has on the chat, on the Google Meet session, or Polly talked about during the Google Meet session. Let's see. So the PA workstation firewall is off earlier this morning, and the exam accounts are ready. Its username is your student ID, and the passwords all the same, f23-inet. So you want to log in and change that immediately. Otherwise, any student can log into your account and do something. All right, so make sure you read the exam page and learn about the regulation. Definitely work on the older exams. And let's see. The Google Meet session is already ready. It's going to be the same session that we use throughout the semester. The Google form link is not yet ready. It's going to be here, in about an hour before the exam. But it will be locked. It will be closed. You won't be able to start filling the form until Polly says the exam begins. So that's exam 1. All right. So that's pretty much what's going to happen this week. All right. And we do have still a few topics to talk about before we close to chapter 2.5. So let's check out the topics today. DNS. So last week we ended at DNS. We talked about the architecture. It's elaborated, right? Especially the server side. We said that DNS, keeping all these host name to IP address mapping, is a distributed database. And it's so big that it requires 3 levels of hierarchy, if you recall. And this week, we'll start by talking about what are these data stored in the database? Okay, so these are the DNS data records. DNS, more officially, the resource records. So here's the video talking about the resource records. And recall that we talked about 4 functionalities of the DNS, that those are the very basic 4 functionalities. And we'll see 4 types of records corresponding to each of the functionalities. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay? Well, to be more precise, the resource records. Okay? And each look like this, a tuple of 4 elements. This is usually the host name, and this is the IP address. And this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname at the name and IP address at the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup to the ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the 4th service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain, okay? But it's not the top level domain. It's usually the 2nd level domain. The value is the host name of the authoritative name server for that 2nd level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. All right, so those are the types of resource records. What's happening is this, the clients will be querying the host name to IP address mapping or the domain to the mail server mapping. And then the server there, okay, in 3 hierarchies will reply with the mapping. Okay, so there are going to be query message going from the client to the server, and from the server back to the client, the reply messages. So this next video, about 2.5 minutes, talks about the format of these query and reply messages. Next, the DNS protocols messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part. Where the actual actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next in the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID.
In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS server saying, no, that's disable recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. Right? There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now, in order for the receiver to know how many lines, how many records it reads, it looks up here to find out and reads up to this point and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. Right? And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value. There's no TTL. In the answer entries, however, then you see the full RR, full resource records. Okay. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used.
All right. And the last video about the data records and the messages is that once these reply arrive at the local DNS server caches these records as well. Okay, so less than 2 minutes.
DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects, so we could reduce delay, we could save some network bandwidth. You see here, DNS for the same purpose also caches IP name mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. So let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay? Again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out. But the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So DNS caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force.
All right. So if you pay attention to that video, you'll see that there's yet another way to handle the cache inconsistency, which is what? To time out the cache when it's too old. Now, how do you know if a cache is too old? Yeah, one can actually analyze how frequent a particular cached object is edited. So in DNS case, it doesn't happen very often. So 2 days is what they say, being the expiration time of a cached RR record. All right. Now, the very last video about DNS is this. Okay. remember pet book, right? Suppose that you're starting up a company, right? And you know that you need to set up a web server. You might need to set up a mail server, okay, for the customers to reach you, okay, or for the customers to, for example, place orders. But okay, before you can set up the mail server or a web server, there's something else you need to set up, okay, as even more important, more fundamental. That is called the authoritative DNS server. Okay, so this video, okay, tells you when you are starting up a company, okay, what you need to set up. First, the authoritative DNS server, and then the mail server and the web server.
Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup, network utopia. All right, so two things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed, there's a backup. At this point, the registrar there, the network solution there, will try to insert two records. Okay. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server mapping. Good. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an MX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website.
All right, so that's all about DNS. And then we move on to a very interesting topic, peer-to-peer, peer-to-peer systems. Okay, so in this first video, you're here Polly reviewing what P2P communication is like. You heard about this at the beginning of chapter 2. Okay. What's more important is the second part of this first video. Polly will try to introduce an example that is to download files for a network of clients, a network of users. Okay, and that example is going to be the base for us to compare the performance, okay, using a client-server architecture versus peer-to-peer architecture. Okay, so let's start with the first video.
P2P applications. To be honest, this is one of my favorite sections in chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on servers, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, hey, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. Okay. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is BitTorrent, and the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. And there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to end users. Right? Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. All right, so file, one big file, size being big F. So this is the setting.
All right, so now let's try to estimate the file distribution time. So that is the time for all N peers to download a copy of that file, F. Okay.
Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here we need to upload the copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US, and to send N copies altogether, NF over US. And this is the term that we have here, because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is d mean. Therefore, the download time is F over d mean. The smaller the d mean is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over d mean. Now, that's considered an N that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with N increasing? Well, this term suggests the overall distribution time will increase linearly in N. While the minimum bandwidth for downlink might not change all that much. Okay, so potentially the overall delay, if we change N, is growing like this.
Yeah, so that's the file distribution time for the client server mode. Okay, let's check out the file distribution time for the P2P mode.
Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Right? Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over d mean, which we explained. And clients overall as aggregated system, must download NF bits, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. All right. So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If we want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, over the entire capacity, entire uplink capacity of the system. Right? So the distribution time bounded by one of these two terms. All right, now consider again, if N is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n. Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this.
Yeah. Okay, sounds promising, right? Using the P2P architecture. So the last video here is to compare the two quantitatively with the same scenario, same setting.
Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time, right? So the scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, f over u, and let's say that that's 1 hour. And the server uplink rate is 10 u, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Right? Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10 u. Therefore, what? F over u. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall. All right. And what is the total uplink capacity of the system? So user has 10 U. Each client has what? 1 U. So 10 of them, also 10 U. Altogether, 20 U. And how much is this? Half of F over U. And this is what? Half an hour. And is that right? It is right? In P2P's case, 10 users, only half an hour. Okay? So you see, the growing trend, linear in client-server mode, but sublinear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. All right? And this is the big advantage of running an internet service in the P2P architecture over the client-server architecture.
Yeah, so from that setup, you can see that P2P architecture can work amazingly well for a group of people trying to download the same file at the same time. And that is exactly this application that's based on P2P architecture is doing. It's called the BitTorrent. Okay. So there's going to be a peer that's holding the original source file and bunch of other peers who are looking for the file and will be downloading the file. Okay. So BitTorrent. Let me introduce the system a little bit more officially. You will hear about the components, okay, in the BitTorrent system. A tracker, okay, that allows a peer to connect to a torrent. So all these peers on the same torrent share a certain file. Okay.
First example is BitTorrent. The way the file is distributed in BitTorrent is instead of sending one big file at a time, it's divided into smaller chunks, 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. Okay? So BitTorrent. Okay. Now, there's one more entity. It's called tracker. So This machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first, contact the tracker and then tracker in return, giving Alice a list of the peers. And this is the initial set of peers that Alice will connect to. Now, once Alice is connected to the torrent, then Alice can try to explore other peers and then re-establish connections to these other peers. So, tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, yeah, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. And Alice at the beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of the exchange. That could be a bit disturbing. There's a special term for it called a churn. Hopefully there's less amount of these churns, but sometimes it's not really controllable. And in the end, once the peer has the entire file, for a selfish peer, he or she might just leave the P2P network entirely. For those who are more considerate, they might remain on the torrent.
Okay, so you see that BitTorrent works in a very simple way. There's a tracker allowing a peer to bootstrap and connect to a torrent. And we heard in the videos earlier that the distribution time of a file scale better. But what are the catches? Okay, sometimes when you hear something that's too good to be true, they are too good to be true. What are the issues? One, the peers can come and go. Who are these peers? We are the peers, right? If you recall, how come we need a mail access protocol for Bob to fetch emails? That's because SNMP assumes that the receiving side needs to be there all the time, and the regular users are just not like that. You see here, the peers are not like the servers. Okay, they might not be there all the time. Therefore, these UIs, they're sometimes high, sometimes zero, sometimes high, sometimes zero. So these churns, can be a little bit disturbing and compromising the overall performance. Second issue is this, and this is probably worse. There are some of us who are there downloading the file, and after we are done getting all the chunks, hey, why stay on, right? Letting other using my upload bandwidth, to download the same file. Yeah, some of us can be selfish, and hey, it's human nature, part of the humanity. So how do we deal with that? BitTorrent has some interesting mechanisms behind to ensure that the chunks, will remain in the torrent. Even though the selfish people leave or some peers might come and go. And they will also try to ensure a certain level of fairness. Those who contribute more then are allowed to download more. So this is what this video is about, and the longest video today, about 5 minutes. Pay attention. Some of these might appear in the exam questions.
The part that Polly finds the most interesting about BitTorrent is this. The strategy to request chunks and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this. Given a file that many of the peers are looking for, so they'll be downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other, so at any given point in time, different peers might hold a different subset of the chunks belonging to the file. And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. So it's kind of an inventory check. Now, once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now, if you think a little bit more about it, why rarest first? If I tell you, look back the previous slide, the issues we might run into are these, right? A peer might come and go, right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks to a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when BitTorrent downloading can go really, really long. It's not because there's not enough capacity, but it's more. Certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. Right? And another aspect that's interesting is the sending strategy. And I love the name, tit for tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here as an example peer, she will send chunks to others that are sending back to her at the highest rates. Okay? So, hey, if you're generous to me, then I will be generous to you. Okay? Eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate. Will be choked then. These guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate the top 4 every 10 seconds. So those peers who discover that they are choked, they are not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. So optimistically unchoke a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay? Interesting, isn't it? And let me animate tit for tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay, and begin to send also at a high rate back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners, okay? And so you get files faster this way.
All right, so rarest chunk first, and a certain randomized fairness, okay, is what's in BitTorrent to ensure that we get the whole file. Okay, there are a couple questions, or maybe to just confirm. I think Zhenyu was asking whether the distribution time is in the order of log n for P2P. Yes, the optimum time is in log n. And Mikhail was asking, do all the peers in the network have the same information? Mikhail, what do you think? Yeah, you know what? The whole point of having a P2P network is such that we can just, do things opportunistically. Therefore, especially when you have a large peer network, it will be hard to make sure that all peers have the same information. Okay, they don't have the consistent view. And it's better that we do not assume that there's a consistent view of the whole peer-to-peer network. And therefore, you see the importance of doing things a little bit randomly. Okay, so some people even propose to do random various chunk download. As you also see in the tit for tat mechanism. Yeah. If you always go with the one who's the most generous, then those newcomers will never get connected. So, yeah, it's local heuristic. Hopefully, you achieve the global optimum. Okay, so P2P is interesting and amusing for many of us, is because that it's very different. It's a lot less deterministic. There's complexity, and complexity is amazing. All right. And you know what? It's time for quiz 14. And we won't have time for the other application that is based on P2P architecture called Skype. My suggestion is that you can go to the website and find the video about talking about Skype. Okay, that will give you some sense how Skype works. Okay, and today we'll try to see if you guys can complete quiz 14. Okay, let me see where quiz 14 is. I think it's here. Yeah, this is quiz 14. Wait. Okay. Yeah, sorry for the glitches. Let me see. There we go. Yeah, quiz 14. Okay. So this is about BitTorrent. Okay, you heard about how BitTorrent works. There needs to be a tracker, and these trackers are typically just websites. Okay, and when you go on these trackers, you look for a file. Then what returns are the peers that you can connect to that's inside the torrent of that file. All right, so trackers, very important. Without the trackers, you don't get on any of the torrents, okay, on BitTorrent. So there have been all kinds of BitTorrent trackers around, okay, for years. For example, Supernova, Torrent Spy, BT Junkie, etc. Okay, you can see that people are using these BitTorrents or creating these torrents that are not exactly legitimate. But among all these, many of them are gone. Okay, they're just gone. Okay, there's only one remaining, or one of few that are the most infamous and remains. Is this Pirate Bay. So Pirate Bay, let's see. There was a news back in 2015, says this. Okay, Pirate Bay is down. Okay, the domain, I think it's probably piratebay.org. Okay, it's seized by the Swedish court because Pirate Bay was registered in Sweden. Okay, and when that domain name is no longer valid, the server cannot be running. Okay, so hey, DNS lookup won't find piratebay.com. Okay, so, but very interesting. The reporter says, but the site is likely to pop back up again somewhere else. Okay, yeah. So you see, it's easy to take a tracker down, but somehow. Okay, people believe that some of these trackers might come back up. Okay, so it's very easy to bring down a web server, and when you bring it down, then you bring down the torrent. Okay, that P2P network. Okay, now Q1 ask, why are these high-profile trackers shut down? Okay, people are still trying to take Pirate Bay down. Okay, think about it. Q2. Okay, speaking from the point of a peer, from the point of view of a peer, okay, or speaking from the point of view of a pirate, okay, can you make the tracker harder to take down? So these are quiz 14. Q1 is a little bit more straightforward. Q2, gather your teammate and discuss, talk about it. And this is one of these open-ended problems. We are now 10:05. The time is now 10:05. We have only 5 minutes remaining. We'll see if any one of you will be able to type up an answer by 2:09. Okay, so you guys have 4 minutes. Okay, see if you what you can do in 4 minutes. Oh wait. Okay, let's go to Discord, channel W6, quiz 14. Yeah, I see Jeremy already typed something up. And Sophia. Okay, let's see. Okay, the rest of you, feel free to discuss and think. Let's see what Team 2 and Team 3 has to say. So why pirate baits are brought down, right? Because they are used to share, illegitimate content. Yeah. So when the tracker is down, no one can join the torrent. Those who were on the torrent can stay on the torrent, okay? But the newcomers won't be able to join. Yeah, so taking down the tracker is a very effective way to shrink the torrent. So Q2, how do you keep Pirate Bay alive? To move to a country with less okay. Okay, so to move Pirate Bay to a country or a region of the world where the copyright laws is a little bit relaxed. So that's one way. I guess that's probably why Pirate Bay was registered in Sweden first, but then the copyright always get tighter. A lot of ways also keep the same name, but changes the host country regularly. Interesting. So you're saying that maybe you register to multiple countries and you change the domain name from country to country. So piratebay.org.tw, piratebay.org. Maybe RU, piratebay.org.uk, and then you rotate using these different domain names. Interesting. Yeah. Okay, wow, 3 solutions. Another possibility is to divide the website into many sub-websites. I see, one for books, one for movies. This is a very interesting idea, Jeremy. I mean, there could be content that are free copyright. So maybe we could move those into another website, right? That will prevent legitimate use of these content from going down when we take just a random tracker down. Yeah. So those trackers, we don't need to take them down. Okay, they are perfectly legitimate. So maybe we could separate the content by the categories, so that the others won't be influenced if a major tracker is brought down. Love it. Okay. When a tracker is killed, a new one will appear to take its place. I don't know. This is very interesting. Okay, this is very interesting. In a way that human ideas are also very resilient. Okay, those who agree with free sharing of knowledge, free sharing of content. I mean, hey, we all kind of believe things differently. All right, let's see Team 3. Okay, let's see if I guess for Q1, illegal content. Yes, for Q1, obviously, on torrents, one can share illegal content, and it's probably the best for these illegal contents to go in case we want to spread them. because I don't think there's going to be any server there dedicated to share illegal content. Okay, because then that means whoever set it up is responsible. All right. Q2, make sure they don't have any mirrors in any countries. But this is hard, as the creators of the site can just buy a domain in a country. Yeah, so I think the first solution is very similar to what Jeremy was saying. Okay, move the tracker to another country. Maybe usually we go to Africa, Middle East, okay, or the third world countries. Team 1, yeah, copyright infringement. It's copyright because copyright costs this, okay, dollars. When it comes to money, yeah, people are very, very conscious in trying to do the best they can to preserve or to compete. Maybe there's a way to make the system very interesting, Anthony. Hey, we just made the file sharing distributed, don't we? Right? We kind of break a big file into chunks and having the peers storing the chunks in a very distributed way. How about we break the tracker, okay, down to chunks and share among a group of peers that are coming and going? Yeah, you know what? There is a kind of P2P, okay, that does this. Decentralized tracker, okay, decentralized tracker. Look up this thing called the DH, distributed hashing, DHS or THL, distributed hashing P2P network. Okay, so maybe I should reply. So the textbook used to talk about this, but not anymore. It's completely distributed, and it's using a hash function to allow faster searching. Okay. All right, so guys, you know what? It's 2:12. I think we have seen enough of these potential solutions to keep a tracker alive. Okay, very interesting ideas coming from you. And hey, you know what? Let's call it a day. And tomorrow, don't forget, join the exam Google Meet session first. And you will hear Polly releasing the Google form link. And you can begin taking the exams. Okay. Those who have not yet tested your camera, please feel free to stay on for a little bit longer. You can still log in and join the Google Meet session here and test your camera. Okay. With that said, I say goodbye. Okay. See you tomorrow. And of course, for Team 8, 5, all the rest, I'll check on your solutions for Quiz 14. Okay. Okay. Bye. See ya. Doesn't care about IPs, okay. Open source. Yeah. So make it open source and get it circulated in the darknet. Distribute the data and the route of tracking. Interesting. Okay, this is interesting. It's kind of having a tracker for the trackers. Very, very interesting. Yeah, why not? Having a tracker for the trackers. Yeah, a lot of the mirror sites. This is very classic. Yeah, we do this a lot for many of the servers around. Yes. All right, great. Okay. Yeah, closing the stream now. Okay, bye.